Okay, great. So my name is Kieran Murphy. I'm the UTAS Node ACEAS seminar coordinator person. And I think last time I forgot to just highlight that Juha is the ANU representative, and then Fabio UNSW. And on behalf of the University of Tasmania and ACEAS, we'd just like to acknowledge all countries that are participating in this meeting because it's online as well. And we'd just like to acknowledge and pay our respects to their elders and ancestors and the legacy that they left us. And just like to thank Francesco for joining us today. And I'll pass over to Zana for sort of a more formal introduction. Francesco.
Hi everyone, thanks for coming to this seminar. And yes, my pleasure to introduce Francesco. He's a visiting ACEAS scholar at UTAS. Francesco is based at the University of Cambridge normally, and he's the Arnell Fellow in Climate Repair, and he's Director of Studies at Downey College. And he leads a few research groups, one at the Paleoclimate Research Group in Cambridge, and also Climate and Environment Thematic Research Group. Francesco has got his PhD in marine geology from Stockholm University, and he did postdoctoral work at Columbia University in the Doherty Earth Observatory. And his research has covered a wide range of topics in paleoclimate, but in recent years he's focused quite a bit on timescales and how we can best date paleoclimate records so that we can compare records from different parts of the climate system. And that's really what he's going to be talking to us about today. So he has some exciting and innovative methods that can really help us understand how the different parts of the climate work together. So very excited to hear what he has to say. So
thanks so much. Thanks so much, Sana. And yeah, thank you all for coming. So as anticipated, I'm going to mostly be talking about the work that I'm doing with my colleagues, with my group in Cambridge. And I would say probably 90–95% of the work that I'm currently doing is geared towards building timescales, high precision timelines for climate records. And today I'm going to be talking about synchronization, alignment of paleoclimate data, which is kind of a key step in establishing chronologies for climate records. So I'm just going to give you a very brief overview of the main issues associated with correlating, with aligning climate records. And then I want to introduce a tool that we designed, my team and I. It's a machine learning tool that was entirely designed for automating the alignment process of climatic records. But I don't want to make this into like a methodology talk. So I'm just going to give you an entry point to the tool, and then I want to talk about the application. So I'm going to go through 3 case studies and show you some of the potential of how we can leverage this tool to get chronological information behind our climate records. So let's start from the beginning. So probably most of the studies that you stumble upon online, especially if you're a paleoceanographer, if you want to build a chronology, you probably have to rely on type point correlation or visual alignment of some sort of abrupt events or climatic shifts in your proxy data. Okay. This is something that's been bothering me since the early stages of my PhD. I thought, wow, can we be a little bit more quantitative? This is very subjective, right? So you have some proxy data, you have an input and data record and a dated record you want to align against, and somewhat kind of identify some peaks or troughs in your proxy signals, right? And basically you build some sort of like HDAT function, right? And you fit a line through it. Most of the time you're going to use linear interpolation. This is a very crude approach. It's very subjective. It's difficult to reproduce sometimes. And it really prevents quantifying the uncertainty of the correlation. So we don't have any robust quantification of the alignment in between adjacent type points, right? Pretty crude. So there's a big assumption behind this whole process, which is like that whatever we are aligning is synchronous. So sometimes, I've seen studies where they aligning a paleoceanographic record in the Atlantic to, I don't know, Chinese speed time, so a monsoon record from China. So that's a big assumption, right? You're really kind of aligning far field records just to build a time scale. And if you work with ice cores, I mean, that's great. Things are a little bit more straightforward, but you're still relying on time points. And this is just an example of a couple of approaches pinned to ice cores where we can use volcanic records or we can use methane synchronization. So these are truly global events that we can leverage for building ice core timescales. So a little bit better, right? So we're not really tuning climate here. We're tuning something that is truly global, right? So like a volcanic eruption or large changes in the methane cycle. Okay, but we're still relying on discrete time points. So we still don't have a good quantification of the alignment in between consecutive time points. So we wanted to address some of these issues and develop a tool that make it readily available for the community, user-friendly, and that kind of goes a little bit beyond time point synchronization. Okay, so manual tuning of these paleoclimate records. And we called it BSync, which stands for Bayesian synchronization. As I said earlier, this is a fully machine learning algorithm. It's automated, it's objective, yields reproducible alignments. It provides continuous synchronizations. So we're really moving away from time points. We don't need time points. And most importantly, is physically based. So it's grounded on a sedimentation model. So whatever comes out of this algorithm is not just a mere statistical alignment. The uncertainties that come out of the alignment are grounded on a sedimentation model. Okay. So what BSync does, it quantifies the probability of the alignment between an undated input and a dated target, given some prior understanding, some prior knowledge about accumulation rates and their variance. What does it mean? That's how fast accumulation rates change down core. Are we going to have like a stiff age depth model? Or is it going to be a lot of variability, a lot of rapid changes in sedimentation rates down core? We can prescribe this information into our synchronization, all right? And BSync treats the alignment as an inverse problem. What does it mean? Okay, so imagine that we have an undated record. Okay, this is a UK 37 reconstruction from the Iberian margin on the depth scale. And we want to align it to NGRIP, to an ice core record from Greenland, which is on its independent time scale. So all we need to do is to provide some guesstimates for the start and end point of our time series. So we're going to prescribe some, we're going to say, okay, well, this is probably present. This is roughly maybe, 60,000 years BP, plus minus, you can be very conservative with that. Say, well, plus minus 5,000 years. Doesn't matter, right? You can be more prescriptive if you want. Don't have to. And then we're going to prescribe some accumulation rates. This is the distribution. So I should use the pointer. We assign a distribution around accumulation rates and their variance. So what we end up with is some sort of like prior age depth space that looks like this. Okay, so this gray area. So very, very conservative, broad prior age depth space. And we're going to explore this space to find a subspace that optimizes the fit between my input and my target. And this is the results. These are actually the output from BSync. So you can see the median synchronization. So now UK 37, it's on the GICC05 timescale. And you can see that the posterior age depth relationship is much narrower than the prior. So the data are really informing our model. You can see also posterior for accumulation rates and their variance. And here we have the time-dependent uncertainty from the alignment. You can see that's truly continuous. And then something that kind of, I want to point out is that generally the uncertainty of the correlation is higher where there is less structure in the data. For example, during the last glacial maximum, right? A few wiggles. It's harder, it's more challenging to find a robust fit between the input and the target. And that's directly reflected in the quality of the alignment. Right? That's why we have larger uncertainties down here. But this is an example of an alignment between a paleoceanographic record and an ice core. And we also wanted to design a tool for ice core scientists. And it was pretty straightforward, actually, to create a spin-off of bsync. And we generated a tool that's called bsync ice, and is entirely designed for ice core data. And the only difference from the previous version is that we incorporate prior information about ice thinning and lock-in depth on top of accumulation rates. Okay, so you have 3 glaciological variables: accumulation rates, thinning function, delta age, if you're interested in synchronizing methane records. The same idea. This is just an example from some data that were published last year by Mulvaney and colleagues. They used tie points, which are shown here. And they wanted to build a chronology for the SkyTrain ice cores using non-soluble salt, magnesium, against EDML, calcium. So they wanted to put the SkyTrain data onto the EDML chronology, the ACC 2012 timescale. And they use specific tie points, right? And I wanted to see whether bsync could do a better job of that. You can see the comparison between the published age model, which is in the dashed orange line, and the bsync output in blue. You barely see them because they're right on top of each other. And these are the posterior uncertainties of the chronology from bsync and the nominal chronology. You can see that bsync does a much better job than just using tie points, because it's really leveraging the structure in between those tie points. Right? It's truly doing it continuously. Okay, so we're pretty happy with that. And there's so many applications for this. Is just like one example. We can use methane, you can use delta 18, you can do orbital tuning. Later on, I'm going to show you, I've done a synchronization using time beryllium, for example. So there are, if you're interested to know more about this, just please reach out. Happy to discuss. Like, there's so many opportunities and applications for these tools. Okay, this is all the methodology that I want to talk about. Hopefully it wasn't too overwhelming. Are there any questions so far? Yeah.
Yeah, I thought you said that the tie point, just tie point match doesn't get you uncertainties. So where's the Mulvaney uncertainty come from?
Right. Yeah, so they're using Ice Chrono. They use a new version of Ice Chrono.
Oh, okay.
So they prescribe tie points. And then obviously it's like, like a Bayesian age depth model, basically you inflate the uncertainty in between tie points. And you can see it very clearly, right? You can see we're gonna have age constraints. Right, you have the uncertainty kind of blows up. But you can do something similar, but just like leveraging the full structure of your time series. And something that I want to point out, you can use tie points if you want. If you have chronological constraints on your data, you can incorporate that into bsync. You don't have to entirely move away from tie points. If you have robust age constraints, you can feed that into the model, and bsync will take that into account. Okay, so use them as gateways for your synchronization, so to speak.
Sorry, one more question.
Yeah, go for it.
I didn't quite catch it. bsync ice. How does it incorporate the ice thinning and the delta age? Is there some sort of
so you need, yeah, so you need some prior information around that, right? So you can see here actually, you have your prior accumulation rates down core, right? And then bsync will explore this space to find the optimal subspace to maximize the fit between the input and the target. That makes sense. It's the same for the thinning function.
Okay.
Right? All right. So some applications. So this is a study that's been Gosh, so this is a record that I had on my desk for 5-6 years now. I was never happy with the chronology. I didn't really know what to do with it. There's some beautiful paleoceanographic data from a core from the Norwegian Sea. And again, never been happy with the chronology until VSync came into the picture. And the idea is that we wanted to measure radiocarbon at very high resolution from the sediment core for the last millennium, potentially to improve the radiocarbon calibration in this region for paleoceanographic studies. And we also wanted to, hey, hi Paul. Generate some paleoclimatic records that give us some insights into the rate of Atlantification in the Arctic Ocean. So this is a key region. The Norwegian Sea is really like the gateway to the Arctic. It's really linking North Atlantic circulation with the Arctic Ocean. So we're really monitoring, all these warm and saline waters that are steered northward, carried northward by the North Atlantic current or the Gulf Stream. So it's a really key location to get a better understanding of the rate of inflow of Atlantic water into the Arctic Ocean. And the first thing that we did was to work on the core top, establish a chronology for our core top. And you can see the age model up here in the middle. So we use a bunch of different radiometric indicators. Okay, so we have a pretty good chronology back to 1850. We measure magnesium calcium from Globigerina bulloides. It's a plantiforum that thrives in summer, early summer, late spring. And you can see the data in blue and how they compare with air temperature in Norway. These are data from observations. And this is how they compare with tree rings from Scandinavia. Okay, pretty much the same thing. And this is really not surprising because the sea surface temperature in this region is strongly correlated. Sorry, it's the other way around. So hydroclimate in Northern Europe is tightly coupled with hydrographic changes upwind. Okay, this is a map showing the spatial correlation of sea surface temperatures at our coring site with air temperature. Okay. So building on this, we said, well, this is great. So maybe we can use the tree ring data to establish our chronology down core. Right? We use it as a benchmark, as a target against which we can synchronize our magnesium calcium data. And that's really where VSync comes into play, right? So here you can see the magnesium calcium data down core converted to temperature anomaly against tree rings from Scandinavia, right, from Western Sweden. These are two ways of showing the data. So you have the median synchronization on the top. And down here, this is the full propagation of synchronization uncertainty. There's just two ways of showing the data just to get a better sense of the uncertainties involved here. Again, here we have the prior estimates for the age depth function and its posterior. So it's a fairly linear model. So I totally stand behind this. It's pretty robust. We're pretty happy with this. And it doesn't violate the radiocarbon dates that we have for this marine core. So now we have a lot of radiocarbon dates. As promised, we measure a lot of AMS dates from plantiforums. And now they're plotted, they're all the dots there, the blue dots specifically. We have a very robust chronology, I believe, and we can place these radiocarbon dates on an absolute time scale. And they give us kind of a picture, a long-term picture for the last millennium of how the marine reservoir, the radiocarbon reservoir has changed in this region. Okay, so this is very useful for future studies. If you collect a core in the Norwegian Sea, you measure, you have your radiocarbon dates, you want to calibrate them. You don't have to worry too much. We can use our calibration curve. Okay, and that's going to allow you to place your data directly on the tree ring chronology. Right. On top of that, this reconstruction of reservoir change, it's a good indicator of It's a water mass tracer, basically. Gives us information about the water mass source. There are two main sources of water in this region. Obviously, there's the Atlantic inflow from south and North Sea waters from the southeast. So the North Sea waters are generally fresher, colder, younger from a radiocarbon point of view. Okay, so negative values, okay, this is the delta R basically reflect the departure from the mean marine reservoir age of the ocean. Okay, so negative values means younger waters relative to the global average. And we interpret those as coastal waters from the North Sea. But relatively older waters are possibly associated with Atlantic waters. And I also plotted the Arctic temperatures from the pages 2K network, just to give you a sense of this tight coupling between hydrographic changes and Arctic Ocean temperatures. But this is a pretty kind of qualitative type of reconstruction, right? I think we can do much better than that. I really wanted to try to be as quantitative as possible and quantify the different hydrographic contributions. And I have to say, so we have many records from this Marine Corps. We have, well, the C14, obviously. We have magnesium calcium that allows us to reconstruct sea surface temperature. We also have delta 18 data that allows us to deconvolve the temperature signal from the delta 18 and work out salinity. So effectively, we have radiocarbon, sea surface temperature, and salinity from this core. And this data is plotted here now in bins of 20 years. And the uncertainty reflects the full propagation of analytical calibration and chronological uncertainty. Okay, I split it by multi-core, so the core top and the piston core. So we apply a source apportionment model. And the model is based on the composition of two water mass end members, the Atlantic inflow and the North Sea, and three spring tracer signatures, as I mentioned, SST, salinity, and 14C. And you can see for different biplots that the data sits reasonably well on a mixing line. Okay, so what we can do with this is really try to kind of reconstruct the relative contribution of Atlantic water entering the Nordic seas. And this is the reconstruction that is shown in red, pinkish, okay, down here. And there are a few takeaways here. So the main observation, obviously, is that the inflow of Atlantic water seems to sit within the natural range of variability for the last millennium. Here is plotted against a number of other Atlantic Ocean circulation indicators. You have the Gulf Stream reconstruction here. This is a proxy for strength of AMOC. Down here, we have a reconstruction of North Atlantic productivity. This is mainly associated with the strength of the North Atlantic current. Meltwater fluxes in the North Atlantic. And what stands out from this is that the inflow of Atlantic water seems to have weakened by 20-25% since 1850. Okay. And then probably more interesting than that is that there seemed to be a decoupling between Atlantic water inflow and Arctic warming. So the again, the Arctic temperatures from the pages 2K are plotted in gray down here. And you can see there's a good covariability up until 1800, 1850 approximately. And then there's a strong decoupling. Okay, so we wanted to investigate that. And we turned to a CMIC model. And we were interested in analyzing the northward oceanic heat transfer, okay, under internal variability and anthropogenically forced climate change. And what you can see here, so now we have the OHT versus latitude, and you can see for anthropogenic climate change, so we have a quadrupling of CO2, we have a significant reduction in northward oceanic heat transfer up until 50 degrees north, and this is associated with a weakening of the AMOC. However, you can see that there's a slight increase in poleward OHT around 60 degrees north. This is associated with the Nordic seas. So we suspect that this has to do with changes in atmospheric circulation. These are very localized regional effects affecting internal circulation or recirculation of warm water in the Nordic seas. So potentially there's a northward advection of heat driven by changes in atmospheric circulation under anthropogenic climate forcing, which started sometime after 1850. And that would explain this decoupling between the inflow of Atlantic water in the Nordic seas and warming in the Arctic. So maybe we shouldn't call it Atlantification per se. It's just an increase in warm water from the Nordic seas spilling into the Arctic, not necessarily associated with enhanced inflow of Atlantic water. Any questions so far? Yeah.
I have a question. The period beforehand also has a very, progressive gradual decline. How do you explain that? I mean, leading up to, for instance, the little ice age in cold climate.
Yeah, that's a little ice age, right? Yeah, that's a good question. Gosh, I don't want to open that kind of worms, but I mean, there's so many studies, discussing what happened during the little ice age in terms of ocean circulation in the North Atlantic, expansion of sea ice, increased meltwater input. But yeah, what you see is definitely like a cooling in the Arctic and a reduction in the inflow of Atlantic water, which is possibly associated with a weaker AMOC. And there's a whole kind of body of literature focusing on the transition from the end of the little ice age to the post-industrial climate changes, and sort of legacy phenomena taking place here, which I'm not going to. I don't think I'm qualified to talk about that. But there's a lot going on. There's also the contribution of volcanic forcing. That's definitely playing a role. So yeah, it's a fairly complex picture. It's a very delicate period, but that's the whole idea, right? You're trying to get a better understanding of what is natural, what is anthropogenic. Where would we define the boundary between these two time periods? Any comments, questions? No? Should I carry on? Okay. All right. Next case study, we focused entirely on ice cores. And this is something that I've been working on for a few years now. We generated a new time-varying record from Waste Divide, and we wanted to put it to use. And we weren't sure what to do with it. And so the first thing to do with such a record is probably to improve the synchronization between Antarctica and Greenland. So we have this record for the deglaciation, pretty high res. And the idea was to use it to synchronize the Greenland ice core chronology and the Waste Divide chronology. So if you're not familiar with time beryllium, this is a proxy for changes in solar activity. So time beryllium is produced in the upper atmosphere from the impact of cosmic rays, which are modulated by changes in the geomagnetic field over very long timescales, so millennial, multi-millennial timescales, and even longer, and changes in solar activity on multi-decadal to centennial, multi-centennial timescales. So that's really what we are interested in. And we can use this signal, we can use this variability to wiggle match time beryllium data from different ice cores to place them on the same consistent timescale. Okay. So this is our Waste Divide record up here in red. And this is the raw data. And this is the data from Greenland. It's a combination of, it's a stack of GRIP and GISP2 data, okay, that was previously published. So you can see there's a lot of structure in the data. We're not interested in these long-term variations. These are probably, climate-related effects. We filter all that low frequency variability. We're really interested in the centennial, multi-centennial scale variability, which is mostly solar induced. That's the signal that we want to align. And we basically end up with something that looks like this, right? So once we filter the data, we get all these wiggles, and that's what really we want to match. This is actually the output from vsync after synchronization. So here's basically the data on the median synchronization, okay? And down here, this is the key figure probably, is the offset, is the time difference between the two timescales once we have synchronized them. What does it mean? So positive values means that the waste divide chronology contains more ice layers than the Greenland ice core chronology. Okay, so it's older, and Greenland is younger. And what is really cool about this is just actually our synchronization is swinging through roughly the independently estimated methane bipolar match points, right? But it's continuous. Okay, so this is consistent with the methane synchronization, but we do it in a continuous fashion. Also, something that stands out from these results is the fast stretch of the Greenland ice core chronology during Heinrich Stadial 1, right? Around 16,000 years before present, of approximately 370 years, meaning that the Greenland ice core chronology is almost 400 years too young. So it means that whoever built that chronology undercounted the ice layers during this cold interval. Now, this is very useful. This is interesting because it allows us to kind of get a quantitative assessment of the ice layer counting for ice cores. However, we're always comparing the input against the target, and we're assuming that our target has a perfect chronology, right? When we do a synchronization, we're always assuming that our target has an absolute chronology with virtually no uncertainty with it, which is a flawed assumption, right? But with vsync, what we can do, we can use it as a chronological tool rather than a synchronization tool. What do I mean by that? Now we can estimate, we can simulate chronologies for both Greenland ice cores and Antarctica ice cores independently. And for each given output or simulation, we can quantify the match between the 10 billion data in Antarctica and Greenland. So what we end up with are two semi-independent age models. So here you see prior and posterior accumulation rates. Okay, so the posterior basically reflects that space that best match the 10 billion data here. And here again, we have a similar plot as the previous slide, but what is shown is the posterior layer miscount associated with each ice core. So it turns out that, yes, Greenland ice core chronology undercounts some layers during Heinrich Stadial 1, but not 360. It's actually 170. And at the same time, the Antarctica ice core chronology is overcounting 200 years, 200 layers. Okay, so it's a compound effect. This is a much more powerful way of using vsync, right? Give us much more information about the miscount associated with each ice core. Anyway, this was a little bit of kind of a fun exercise to do, just to get some insights about how wrong we are when we're counting ice layers in ice cores. So if we're happy with our beryllium 10 synchronization, now we have Greenland and Antarctica on the same consistent timescale. Okay? But that means that effectively we have very many delta 18 records on the same timescale. So we have at least 10 ice cores, 5 from Greenland and 5 from Antarctica. These are internally synchronized using volcanic markers. And now they're all on the same timescale. And we can do, we can have some fun with this data, do some PCA, try to extract some, the common variability across this wide range of ice core records. Obviously, we propagate all the sources of uncertainty, especially the synchronization uncertainty. And what we come out with are two main signals. We have a first principal component, which resembles global radiative forcing. And that explains 80% of the wiggles in the data. And then we have a second mode of variability, which looks very much like AMOC. Okay, and this explains about 10% of the wiggles in the ice core data. And here you can see the associated EOF, so the spatial pattern of the two principal components. So the AMOC has a clear bipolar structure, right? Positive loadings in Greenland and negative in Antarctica. Also, something that's really, really interesting is that you can really see there's a lot of structure during higher stadial 2, which is really not clear if you're taking, you know, all the Delta 18 records from Greenland, right? A very subdued signal during higher stadial 1. Anyway, so but that's not that important. But we turn to transient simulations of the last glaciation. We can use the trace simulations to test to do basically an attribution analysis, since trace now incorporates stable water isotope. We do a similar exercise as we've done with the ice cores by using model data, work in the model space. And we're looking at the principal components for single forcings, okay, for freshwater only, greenhouse gas forcing, and changes in ice sheet topography. And basically, this is consistent with our initial interpretation. So you can see the data-based PC1 in gray and the model output in orange. So this is this first mode of variability is associated with greenhouse gases, okay? And the second one seems to be associated with freshwater forcing. Okay, so it's consistent with this idea that our second principal component reflects changes in the strength of AMOC. So this is interesting. So we can now finally have some sort of signal or reconstruction of changes in AMOC in the Atlantic, right, for the deglaciation. What are we going to do with it? It's a qualitative reconstruction of the timing of AMOC change. And we can incorporate it with quantitative model-based reconstructions of AMOC change during deglaciation. Okay, so we can combine these two types of lines of evidence. We have the absolute changes in AMOC from model-based estimates and the precise timing from our ice core analysis. And we can combine them to reconstruct rates of change, or AMOC. And we place them into the CMIP6 projection context, just to give us some insights about how fast and how much AMOC changed during deglaciation compared to future projections and also historical simulations. Basically, the takeaway here is really like the range of variability of AMOC across these rapid climate shifts, right? HS1, Olin-Alarid, Younger Dryas, early Holocene. It sits really within the projected AMOC change for the most optimistic and intermediate emission scenarios. Bit of a work in progress, but yeah, this is the main takeaway from this exercise. Any comments and questions?
Maybe just, does anyone online have any questions? Or they tend to be a bit shy?
They're a bit shy, right? Yeah, I'm very shy when I'm like that. All right, I'm almost done. Bear with me 3 more minutes. Okay, this is my last case study. I'm really excited to show this. I haven't shown it before. This is a project that we started a couple of years ago. This is a NERC-funded project where we tried to use Tambourine, meteorite Tambourine in marine records for the first time at very high resolution. So the idea is try to leverage potentially the solar signal in marine Tambourine as a tool for synchronization against ice cores. So one of the main issues that we have in marine records and paleoceanographic records is to establish a chronology. We can't use radiocarbon in a straightforward way as we would for lake records or peat bogs or whatever. It's very complicated. We always have to rely on alignments or climate tuning or climate alignment, whatever you want to call it. So here we want to provide some sort of like independent tool to link marine cores to ice cores, to place them on an absolute time scale without relying on climate tuning. And this is just an example, one of the many data sets that we've been producing. Again, this is a marine core from the Iberian margin. Our data is plotted here in blue. So this is a 10 beryllium data at 1 centimeter resolution, spanning. So we're kind of looking at deglaciation again. And here is plotted alongside a bunch of XRF data, okay, just to give you some context. And the first thing that we do is try to kind of use all these proxy data that we have from our core to remove any potential depositional effect on the 10 beryllium. So we use, so basically we remove the covariability with XRF data to kind of filter out any environmental influence. But this doesn't really matter that much. So you can see here actually the row and the corrected data. And this is really good. So we have very large shifts of approximately 30% in 10 beryllium, which is comparable with what we see in ice cores. So that's very encouraging. And then we use our data to align against ice core 10 beryllium. Okay, and here I've used our data from waste divide, which is plotted in black up here in the background. And you can see that our data obviously is kind of like a smoothed version of it, right? Obviously, there are some bioturbation effects on marine sediments that we should factor in, but there is some signal, there is some structure that can be correlated, right? So this is the output from BSync. This is the posterior age depth function, reasonably linear. I don't know if that's a good thing or not. My experience, it's something encouraging. And then I also plotted some proxy data on the synchronized timescale against waste divide methane. I use methane here because it's the closest thing to a Greenland climate record that we have in Antarctica, right? I can't use delta 18 because that wouldn't be a truly North Atlantic signal. But just to give you some kind of temporal context for what's going on in the proxies. And I also propagated the synchronization error into the XRF data. So this is calcium titanium, which is an indicator of terrestrial runoff. And you can see that's fairly consistent with the climatic framework for the North Atlantic. There might be some relative phasing during the younger dryas, not sure what's going on here, but it's more or less consistent. And this is really good news because it's telling us that, yeah, maybe we can use climate synchronization, right, for these records. It was an untested assumption. We always do it. Just making this assumption that we can correlate signals across very, far afield regions. But now we can actually quantify it and test it. It's a valid assumption. It seems to be the case. All right, that's all I have for you today. And just going to leave you with my main conclusions. And yeah, thank you very much for your patience, and I'll be happy to take any questions.
Thanks so much, Francesco. That was really great. Awesome figures throughout as well. It's beautiful.
A lot of colors.
And just gonna go to online first to see if anyone has any questions or discussion points from online. Don't be shy. Turn on or put on your mics and let us know. So we've got a question from Marilla.
Hey, thanks for a great talk. I was interested in your second study where when you broke down the difference in the chronology between Greenland and Antarctica, that it looked like they both kind of went off course at the same time and by the same amount in opposite directions. And I was just wondering, is there sort of like a climate sort of mechanism to explain why those errors seem like they're not unrelated from each other?
Yeah, that's a really good point. I didn't think, well, I haven't really elaborated this too much, but yeah, I guess the idea is that during higher stadia 1, which is the time interval when you have these massive changes in overcounting, undercounting, depending on the ice core that you're considering, climate is really cold in the North Atlantic, so that kind of tends to, this basically results in a miscount, because it's much easier to miss layers because they're very, very thin, right? Whereas in Antarctica, that's a period where you have relatively higher accumulation rates, right? Through the bipolar seesaw, right? So it might be easier to overcount in that case. Yeah, I think I probably would ask that question to an ice core person, but that's my very basic, crude understanding of what is going on there. But it's not surprising, and I'm really happy to see that actually, we haven't missed almost 400 years in Greenland, but it's a combination of things. So that's more in line with, with the nominal counting error of the Greenland ice core chronology. So we can deal with 170 years. 370 is quite a lot.
Great. Any further questions online, or I'll look around the room?
I'll just ask a very nerdy question, I guess, but have you considered using thorium-230 in difficult years? Like, I think it might help with the brilliant end, or even synchronization assumptions, some models that like incorporate that into type of that at all.
We had an ongoing conversation whether to use thorium-230 for constraining SED rates. But I don't know, for the IBR margin, well, we have so many, proxies and lines of evidence, and so we've got pretty good grip on sedimentation rates, just looking at the climatic stratigraphy, basically. Delta 18, we have a lot of C14 dates that also help us to kind of ballpark the chronology. Yeah, it is a good point. It's probably like, for a much longer chronology, I don't know if I work like spanning MIS3, like 50,000 years chronology, I'll probably incorporate all the possible age constraints and using
Maybe areas
yeah.
we don't have forums.
Well, IBR margin is fine, but if you go like in the North Atlantic during cold periods, it gets a bit tricky. But yeah. Yeah, I think I mentioned that in the proposal, but then we never really pull it off, probably.
Kind of maybe simpler question, or just a basic question about the methodology. When you did the initial transfer from BSync to BSync ice, and you compared it to, was it McIntyre or?
Oh, the data that I showed now.
Yeah, in one of the first slides. Like, were you surprised at how well it accounted for? It was more certain than the ties sort of methodology, the correlation methodology, based on it using like a sedimentation model, or?
I felt really good.
Yeah,
I felt incredibly good. So, oh wow, I wrote something that works. Yeah, no, I wasn't surprised, because that's the whole point. So, okay, it works, great. That's but
the transfer from kind of a sediment core to ice core, like, would that be expected, or the same kind of assumptions? And
I mean, it's a there's some kind of simplistic assumptions, but yeah, you do have accumulation of snow. You're doing like, it's just a simple sedimentation model, whether it's mud or it's ice. Yeah. It's more, I mean, I want to say it's more or less, it's not the same, but for ice cores, that's why we incorporate also the thinning, because you need to strain these ice layers. Potentially you can add, other, there are so many like additional layers of complexity that you put on top of the model. But this is the simplest version of it, given some prior basic understanding of how your ice core accumulates over time. Yeah.
Yeah, cool. And how do people is this a freely available model? Like, how do people actually implement it?
Right. So we're still developing a package. The idea is that we're going to have an R and Python package, hopefully by the end of the year. My postdoc Marco in Cambridge is currently writing up the manuscript. So BSync, the basic algorithm for proxy synchronization, is hopefully it's going to be published soon. But for BSync ice, we're still a bit of a work in progress. Also, it would be really nice actually to get feedback from ice core people to help kind of sharpening up this tool. Yeah.
Oh, I can't help you go back to that AMOC graph, but I just wonder, because I think a lot of people who work in the contemporary side of things think this 25% reduction is like the equivalent of hockey stick climate.
It's a lot, right?
But you've got a lot of variability in your figures. I just wonder what's an alarming.
It's not too
rate
far
of
off,
change?
actually. So there are. So think about like, was it like a. So Matt Osmond published a paper a few years ago. They showed that this was like 20% reduction in ocean productivity in the North Atlantic, linked to a slowdown of the North Atlantic current. For AMOC-based reconstruction, that's pretty much in the same range, 15–20% reduction since 1850. So it's not too far off. I mean, this is the. I mean, you have to factor in uncertainties as well. So probably 25%, maybe it's a little bit, extreme. But we're looking probably somewhere between, 10 and 25.
But before that, you have a 50%.
You have a 50% reduction. Yes,
So
you're right.
it means that if what should we expect? What's the range of natural
Variability.
before any greenhouse gas influence?
Yeah, it's a good question. We need a longer record, I guess. Yeah. Yeah, sorry, I don't have a straight answer for you, but yeah, I guess probably need a longer context. Any other question? We have one over here, maybe?
Yeah, a little more technical question on study 2. So you did the use BC ice.
Yeah.
And you found the chronologies for GIC scale 5
Mhm.
and
Yeah.
But then you took a bunch of the ice core proxy records and this EOF.
Yeah.
For attribution. Basically one mode looks like AMOC radiated force.
Yeah.
I think you would have found that anyway. Without the whole BC thing.
Yeah,
So
you would.
I just sort of lost like what is it?
No, you would. So I mean, this is kind of that's nothing new, right? So we know if you chuck in all the proxy records that we have for visualization in your PCA, you get the same 2 modes, but a much lower resolution. So the benefits of doing here is that we can really leverage all these high res delta 18 data, and you know that you have a very precise timeline for whatever abrupt event you pick up in these PCAs, right? Whereas if you're looking at other studies, I don't know, like Shakun, Osman, whatnot, I mean, they have like 250, 500 year bins for their reconstructions. You do capture the same pattern of variability, but you can't really put your finger on the timing of these events. Whereas using ice cores, it's a different story. So that's the edge, I guess.
Yeah. Okay, and just a comment if you want ice core feedback. I have a ton of
Good.
data that we
Bring it on. Yeah.
subjective pipeline.
Cool.
They run it through BC.
Nice. Music to my ears. Yeah.
On the beryllium in marine sediment, I don't know anything about beryllium, but is there anything about the chemistry of beryllium in the ocean that means you wouldn't expect like a direct kind of lineup of that in the ocean versus in the ice sheet? So just thinking about what its presence time is, chemistry or other things. You said try to remove some of those environmental.
It's a very crude approach, admittedly. There are a bunch of processes that may be affecting the concentration of beryllium. Terrestrial runoff, from continental ice shelves or whatever. Just like so that's why actually, so the beryllium, the marine beryllium community, what they do, they generally apply some sort of normalization using thorium, or they used beryllium-9. Ideally, the more proxies you have, the better. So you can really tease out anything that is not a cosmogenic production signal. But at the end of the day, we don't know, because we're really at the forefront here, because nobody has done like 10 beryllium at this resolution. What is encouraging is that there are these major shifts of 20, 30%, which are really, really large and then comparable with what we see in ice cores. I have colleagues working, doing this kind of stuff in the Arctic and high latitude North Atlantic, and you don't get anything that looks like that. You have variations of 5, 10%, which is really just above the noise threshold. And there are a lot of contributing factors from meltwater and whatnot. So it's really, really difficult to tease out a consistent signal that you can use for synchronization. So there are a lot of secondary processes at play. But the Iberian margin is just a phenomenal place. Everything works there. I don't know. It's just just great. Whatever proxy you want to develop or want to measure there, it just works brilliantly. Yeah, that's why I went straight for that. Right, you guys done grilling me? Yeah.
Yeah.
Thank you for your attention, guys.
Please just thank Francesco once again for a great talk.
Thank you.
I'm sure you can reach out to him by email. If you have any more CIs or ice core people.
I'm around until July, so
Awesome.
yeah, please come and find me. Thanks, Kieran, for organizing.
Thank you. And the meeting, and that will go.